So today I'm going to talk about this method that we developed with my colleagues, David Duché, Marcel Pasquinelli, Léo Poughon, Stéphane Viollet, and Julien Serre. So it's a method that we call SkyPole, and that is aimed at finding geolocation information with skylight polarization and without using a satellite system. So I'll start by putting this work into context, and after I'll present you the SkyPole method. So for the context, we are working on global navigation satellite system denied navigation. So why are we working on such situation? Because GNSS are not always reliable. They can be disturbed either voluntarily by spoofing or blurring, or involuntarily by the presence of obstacles that can reflect or mask the GNSS signals. So this issue can be dramatic for some applications, such as autonomous vehicles or military. So alternative solutions exist. For instance, on autonomous car, we can use lidars, cameras, radars, but those alternatives, they require a prior knowledge of the environment. We also have inertial navigation sensors that provide our actual position with knowing the initial position. However, inertial navigation sensors, they suffer from a signal drift in time that leads to an error accumulation. So alternatives also exist in nature. So animals, they also need to navigate, but they do not have access to GNSS. So we focused here on migratory birds that are incredibly good at navigating. They are able to go from a really high latitudes in the north hemisphere to very low latitude in the south hemisphere. And the question is, how do they do to navigate? What information do they use? So some studies already asked this question, and they suggested that migratory birds, they have shown that migratory birds, some use a magnetic compass to find the magnetic north, and a star compass that provides the true north. And they use this star compass to calibrate the magnetic compass, because the magnetic compass gives the magnetic north, which drifts in time. So how do they use this star compass? They use here what we call the celestial rotation. So since the Earth spins around itself, if we look at the sky for a long moment, we'll see that all the stars turn around the point, and this point, we call it the celestial pole. So north celestial pole for someone who is located on the north hemisphere. Else we'll talk about south celestial pole. For the following, I'll just talk about north celestial pole, but it will be the same. So what's interesting about the celestial pole is that when we found it, we directly obtained the direction of the north, the true north, and its elevation with respect to the horizon gives our latitude on Earth. So whether we are closer or further from the Earth equator. Studies also suggest that birds can calibrate their magnetic compass during day by using the skylight polarization. So skylight polarization can be described by Rayleigh scattering. So Rayleigh scattering occurs when sun rays enter the atmosphere. Those sun rays will interact with particles from the atmosphere, and those particles will scatter light in all the directions. And what's interesting about this is that the scattered light will have a polarization property that will depend on the direction of the sun rays and the direction of the scattered light. So we unfortunately cannot see the skylight polarization, but we can observe it using polarimetric cameras, and we can extract two patterns, a pattern of angle of polarization and a pattern of degree of polarization. which are both related to the position of the sun. On for the method, I only focus on this degree of polarization. So let's have a look at how this pattern evolves when the sun moves in the sky. So during day, as during night, we have this pattern of this sun that moves due to the rotation of the Earth. And if we look at the skylight polarization, we have here this degree and angle of polarization represented in fourth color that move with the sun. However, we do not really see here how we can find information on navigation just by looking at those two patterns. And so the question we can ask is, how can this skylight polarization be used to calibrate a magnetic compass? So here, biologist studies didn't give precise information on how animals, birds can calibrate their magnetic compass during day. So we developed our method using only theoretical models of the skylight polarization. So to do so, we use two assumptions. First, that the sun moves in a plane which is perpendicular to the observer north celestial pole vector. The second assumption is that the skylight polarization can be described by a Rayleigh scattering model, which states that the degree of polarization depends only on one variable, which is the scattering angle, which is the angle between the sun, the observer, and the point of observation. And what's interesting about when we merge both assumptions is that since the sun turns around this celestial pole, if we look at the scattering angle between the sun observer and celestial pole, it is constant along the day. And so we have therefore this degree of polarization at the north celestial pole that is invariant during a whole day. So I wanted to see if other points had this property. And so we took two degree of polarization images of the sky, and we just computed the absolute difference between those two patterns. And so we see here these patterns that appear with two circles, one here and one here. And a circle on which the degree of polarization didn't change between those two moments. So here we have the sun at the first line, at the second line. And so we have this celestial pole that is located on one of the invariances. So those invariances are linked to symmetries of the skylight polarization pattern. So if we look at this difference pattern during a day, so in green and yellow you have the two positions of the sun used to compute those invariances. And so we see that this invariance always goes through the celestial pole, and we can show that the celestial pole is the only point in the sky that has an invariant polarization during day. So we proposed, based on those information, we proposed an algorithm that we wanted to keep as simple as possible. So it could be, in a way, processed by animals, even though we don't know, but keeping this algorithm as simple as possible. So the idea was just to take some images that you can see on the first line here. So you have some polarization skylight images. Then we process the absolute difference on the second line. This step is not mandatory, but it's more visual. We can separate the invariances from the background, and we obtain the position of the celestial pole at the intersection of all the invariances. So we tested this method with a polarimetric camera located on the rooftop of a building in Marseille, France. So here we can see that we visually have something that looks like the theory with the radial and with the invariances that appear. And here we have our results in, so here we have the azimuth of the celestial pole that gives the direction of the north, and here the altitude of the celestial pole that gives our latitude. So we'll discuss about the errors that are quite big, but we can see that the results are validate our hypothesis. One issue about this algorithm is that sometimes we can have multiple intersections of invariants. If we take, see here, we have some other intersection of invariances, and so we can have an ambiguity. And just to show you, we can use another type of algorithm to separate the what we call the radial invariance from the plane invariance. And so I remind that the celestial pole was located on this radial invariance. So here we have no more ambiguity because we have just one intersection of invariance that is possible. So we can do it by using here a neural network that will isolate this invariance from two skylight polarization patterns. And so we tested this method on a 1 month dataset that is open access. I'll give you the link at the end of the presentation. So to discuss quickly this method, so we used images that had time interval that was quite long, more than 30 minutes. So this is quite long to geolocate. We can reduce this time, but with some data processing, because the main problem when we reduce the time is that it's harder to distinguish the invariances from the background. So we have to work on this data processing. And just here we only used a simple median filter on the images, so no other processing. And for the precision, just so you have an idea, 1 degree error in latitude is about 100 kilometers of error, so which is quite huge. And here, 1 degree error in azimuth is seems less to be an issue, as you can see on this image. So to finish, here is an image that represents the celestial rotation during night with stars and during days with this pattern of polarization. And the celestial pole is located here at the center of rotation. So thank you very much for your attention. Hope you enjoyed the presentation. If you have any question, I will be glad to answer. And just to finish, I have here 2 links, one to the article that we published, and one to the open access dataset that is available for free. Thank you.